Hello, everyone, welcome back to the channel War Horizon. Please subscribe and like my videos. Today, we are diving into one of the most shocking and intense fictional battlefield scenarios ever discussed on this channel, centered around how 200 Ukrainian Convoy drones allegedly erased an entire North Korean convoy during a hostile support mission to the Russian front line. This story may be fictional, but it is built around realistic engineering concepts, battlefield tactics, and the evolving nature of drone warfare that has changed modern conflict forever. What makes this scenario so dramatic is not only the scale of the attack, but the incredibly improvised yet extremely effective design of the drones. Crafted in workshops, garages, basements, and underground labs scattered across Ukrainian territory. These drones were not state-of-the-art military equipment from major manufacturers. Instead, they were community-built machines assembled with off-the-shelf components, custom-made frames, open-source flight controllers, and a dose of raw battlefield ingenuity that has become a hallmark of modern asymmetric warfare. From the exterior, these fictional Ukrainian Convoy drones were intentionally deceptive. Their bodies were made from lightweight carbon fiber and polymer composites, often sourced from hobby stores or repurposed from commercial drones. Some used simple plastic shells reinforced with strips of aluminum, giving them a rugged structure capable of withstanding harsh conditions. The overall footprint was compact but intimidating, with 4 to 6 motor arms extending outward like skeletal limbs, attached with custom machined joints or even 3D printed connectors that offered both flexibility and resilience. The paint scheme varied from drone to drone, but most had matte, black or sand gray exteriors designed to absorb light instead of reflecting it, making them far less visible during dusk or dawn operations. A handful of drones were camouflaged with digital patterns, while others carried nothing but raw composite color, showing the simplicity and rawness of their battlefield purpose. The placement of the propellers was also intentionally unconventional. Instead of evenly spaced traditional quadcopter arms, some drones used asymmetrical layouts that improved maneuverability and stability when carrying heavy payloads. These payloads ranged from small anti-personnel charges to shaped explosive canisters capable of piercing armored roofs. On the underside of the drones, modular bays allowed operators to attach, detach, or adjust the payload within minutes, demonstrating the flexibility required in a fast-moving conflict scenario. Another exterior detail that stood out was the extended battery compartment, shaped like a slim, rectangular box strapped tightly under the main fuselage. This allowed the drones to carry upgraded lithium polymer cells for longer endurance, with some units using dual battery configurations for extended range and loitering time. Moving deeper into the interior of these fictional drones, the level of innovation became even more astonishing, and this paragraph will be big as you requested. The heart of each drone was a compact but extremely reliable flight controller, usually based on open-source firmware like Ardu Pilot or Betaflight, modified by Ukrainian technicians to prioritize communication, resilience, and advanced flight autonomy. The wiring inside the airframe was carefully arranged to maximize efficiency. Twisted power leads for minimal interference, heat, shrunk ESC connections, and a reinforced wiring harness that allowed the drone to remain operational even after suffering minor shrapnel or gunfire damage. Some drones used vibration-isolated platforms mounted on dampening rubber pads to protect the IMU and accelerometer sensors from oscillations caused by the powerful motors. The power distribution board was often custom-etched on site, meaning that every drone had a slightly different internal architecture depending on which workshop built it. Despite these variations, the overall functionality remained consistent. The drones were designed to remain stable, responsive, and resistant to jamming. Inside the communication bay, technicians installed long-range digital transmitters, often modified from commercial FPV or RC systems. These transmitters worked in conjunction with mesh network receivers, allowing the drones to operate in coordinated swarms without relying on a single control center. A critical element of the interior design was the dual-layer electromagnetic shielding inside the fuselage, created by lining the inner shell with thin metallic sheets or conductive paint. This helped protect the flight electronics from interference and attempted jamming by opposing electronic warfare units. The navigation system used a hybrid setup, combining inertial measurement, optical flow sensors, and, when available, satellite positioning. This layered navigation allowed the drones to fly through GPS-denied zones by relying solely on visual markers and internal orientation. The battery management system was another remarkable feature. It monitored temperature, voltage, and power draw, giving operators real-time feedback and allowing drones to autonomously reroute or return if they detected critical power levels. Inside the payload bay, specialized mounts made from aluminum brackets or 3D printed ABS plastic held explosives securely in place. These mounts incorporated quick-release mechanisms triggered either by remote command or automated impact sensors. All these interior components worked together to transform improvised drones into precision-guided battlefield assets capable of executing complex missions. When it came to performance, the fictional swarm of 200 drones demonstrated why DOA systems have become one of the most feared innovations of modern conflict. The drones had an effective operational range of up to 25 kilometers, depending on the battery configuration, and could maintain top speeds approaching 100 kilometers per hour in dive maneuvers. Their cruising speed was around 65 kilometers per hour, allowing them to traverse difficult terrain and remain airborne long enough to identify and engage targets. The powerful brushless motors gave the drones excellent acceleration, making them extremely difficult to intercept using small arms fire or anti-drone shotguns. Their maneuverability allowed them to execute tight turns, sudden altitude changes, and evasive zigzag flight patterns that overwhelmed the convoy's defenses. Many drones in the swarm were equipped with low-light optical cameras, giving operators real-time video feeds of the battlefield. Some had thermal sensors integrated into the nose, enabling them to lock onto hot engine signatures from vehicles within the convoy. The performance of the swarm became even more devastating when the drones switched to autonomous targeting, allowing dozens of units to fly in coordinated patterns, isolate targets, and strike simultaneously. This level of synchronized performance, especially in a fictional context, represented the future of decentralized aerial warfare in ways traditional armies were unprepared to counter. In terms of safety features, the Ukrainian technicians implemented several innovative systems to ensure reliability and mission success. Each drone contained a fail-safe protocol that forced it to return to its launch point if communication was lost for more than 30 seconds. In swarm mode, if one drone lost signal, nearby drones could relay commands to it, preventing unnecessary losses. The drones also had built-in thermal protection that automatically reduced motor throttle if temperatures reached dangerous levels. Battery cutoff systems prevented overheating or fire, cutting power if the voltage exceeded safe thresholds. To avoid mid-air collisions during swarm flight, each drone used proximity sensors or internal altitude algorithms that created invisible air corridors, ensuring drones maintained minimum separation distances during flight. This system was not perfect, but it reduced collision rates substantially. Another key safety feature was the impact detonation safeguard. Explosive payloads were designed to arm only when the drone reached a minimum altitude and distance from operators, preventing accidental explosions during launch or handling. These safety features ensured the swarm operated efficiently, minimizing the risk of unintended damage while maximizing operational effectiveness. When discussing unique selling points, the fictional Ukrainian Convoy drones stood out for their affordability, modularity, adaptability, and sheer versatility. Unlike mass-produced military drones from major defense industries, these Convoy units could be built for a fraction of the cost using accessible components while still delivering near military-grade performance. Their modular frame allowed technicians to swap motors, adjust battery configurations, replace propellers, or install new flight controllers within minutes. This made the drones extremely adaptable to changing battlefield demands. The ability to switch payloads, from anti-armor charges to anti-personnel grenades or even electronic warfare modules, gave them a multi-role capability unmatched by conventional systems. Another unique advantage was their swarm intelligence. The drones could coordinate with each other using decentralized communication protocols, forming a lethal network that rendered convoy defenses nearly useless. Their stealthy acoustic profile, lightweight construction, and small radar signature made them difficult to detect until it was too late. Most importantly, these drones could be built in large quantities with minimal resources, making large-scale swarm attacks feasible even under wartime constraints. As for price, the fictional Convoy drones cost between $400 and $1,200 each depending on configuration, materials, and payload. Some high-end versions with thermal cameras or advanced communications systems could reach $2,000, but even at this upper end, they remained vastly cheaper than traditional guided munitions. With 200 drones averaging roughly $800 each, the entire swarm cost less than $160, an astonishingly low figure when compared to the multi-million-dollar armored convoy it allegedly neutralized. This low cost allowed Ukrainian technicians to build large quantities quickly, making swarm warfare sustainable and scalable. In conclusion, the fictional scenario of 200 Ukrainian Convoy drones erasing a North Korean convoy serves as a powerful demonstration of how improvised engineering, battlefield creativity, and decentralized drone manufacturing can reshape the future of warfare. These drones may be built from humble components, but their design, performance, swarm coordination, and devastating combat capability highlight the unstoppable rise of drone-based asymmetric tactics. The event may be fictional, but the technology, principles, and implications are very real. Modern warfare is no longer determined solely by large armies or heavy machinery. It is increasingly shaped by small, fast, intelligent, and expendable flying machines built by everyday technicians. If this scenario teaches us anything, it is that the future battlefield belongs to whoever can innovate faster, adapt quicker, and turn simple machines into unstoppable strategic forces. Thank you for watching. Please subscribe to War Horizon and stay tuned for more deep dives into the evolving world of modern warfare technology.